As I had discussed in my earlier lecture, that the Pelton wheel is nothing but an impulse type of turbine which is well suited for operating under high heads. It's also known as a tangential flow turbine because the jet of water that issues from the nozzle will strike the pitch circle, and pitch circle is nothing but the line joining the centers of the buckets. And since the jet of water strikes tangential to the pitch circle, therefore it is also known as tangential flow turbine. So here the runner consists of a circular buckets which are mounted on the periphery of the runner, but these buckets have a shape of a semi-ellipsoidal cups, double semi-ellipsoidal cups, and each bucket is divided into two symmetrical parts by a sharp edge ridge known as splitter. So here one or more nozzles which are fitted at the end of the penstocks will direct the jet of water along the tangent to the circle, which is known as a pitch circle. And this pitch circle is the circle that is passing through the centers of the bucket. So when the jet of water impinges on the splitter divides the jet into two equal portions, and each of which after flowing through the inner surface of the bucket will leave at the outer edge. So in this case, the buckets are so shaped that the angle at the outlet tip will be around 10 to 20 degrees, so that the deflection angle is around 160 to 170 degrees. So now this figure shows the Pelton wheel. So you know that, as I had explained, so it consists of a double semi-ellipsoidal cups. Okay, so this is the shape of the cups which are mounted on the periphery of the runner. So therefore this cup is divided into two parts by means of a splitter. So water comes and strikes the splitter and then moves tangentially like this, or glides over the inner surface and moves out at an angle 10 to 20 degrees. Okay, so this is here. So the line joining the centers of the buckets like this is known as the pitch circle. So is known as the pitch circle. Okay, so this here it is very clear, so that we have the buckets that are mounted on the periphery of the wheel. So therefore if we join the centers of the bucket, so this is the pitch circle. Okay, so now the jet that is coming out of the nozzle will strike tangent to the pitch circle, will tangent, so that's why it is known as, also known as a tangential flow turbine. So another figure shows that the jet is striking tangent to the pitch circle. Okay, so we have buckets, okay, which is shown in plan. So therefore we have the buckets is a shape of a double semi-ellipsoidal, so two parts, two symmetrical parts are there, which is divided by means of a splitter. So now when you take a section like this in this fashion, so we have here the vein. So now a jet of water, so as it is issues in a straight line like this from the nozzle and hitting tangent to the circle, so therefore the inlet velocity triangle is always a straight line. So now this is the incoming direction, this will be the outgoing direction. So now when the jet of water is about to strike, so the vane would have moved by with velocity u. So therefore the velocity with which it is striking is nothing but Vr, which is called the relative velocity. So hence Vr is nothing but V minus u. So it strikes with Vr velocity, that is V minus u, and comes out with velocity Vr1. So Vr1 can be is always less than Vr, because there is some loss that takes place when the flow takes glides over the inner surface. So now the difference between the angle between the incoming direction and the outgoing direction is known as the deflection angle. This is generally kept 160 to 170 degrees, so that the phi can be around 10 to 20 degrees. So this is what you should. So now this the inlet velocity triangle is, now this is V. So by the time it hits V, the vane would have moved by some velocity U. So therefore line joining from tip to tip is VR. So VR, as from this diagram, is always V minus U. So now you can have three types of diagram at the outlet, as I had discussed in the velocity triangles. So if the jet of water issues along the tangent, so therefore the person sitting on the vane will be seeing that the jet leaves at a velocity Vr1. Okay, so now this angle with respect to the direction of motion of vane is called the angle of vane. outlet. So we know that this is VR1 cos phi. So now here, as the jet leaves in this fashion, then beta will be less than 90 degrees. So therefore VW1 is VR1 cos phi minus U. So here beta is less than 90 degrees. So beta can also be equal to 90 degrees. Then the jet leaves in this direction. So like this at right angles, okay, to the direction of motion of the vane. So then U will be equal to VR1 cos phi. Then VW1 will be equal to 0. So in the case also we have with the jet in leaves in this direction, that is with an acute angle with respect to direction of motion of the vane. So then beta will be greater than 90 degrees. Then VW1 is U minus VR1 cos phi. So these three possible outlet velocity triangles will be there for Pelton wheel, as we had discussed in the velocity triangle. So now you know that the entire mass of the fluid is striking the vanes per second. So it is rho into Q, so rho A into V. So the component of velocity striking the vane at the inlet tip in X direction is VR. So as usual, it is V minus U. So now we can have the component of velocity VR1 in the outlet direction, that is minus VR1 cos phi. But VR1 can be K times VR. So because it can be 0.9 times VR or 0.85 times VR. So therefore, instead of VR1, we write it as K times, where K is a coefficient which accounts for the losses. So K times VR. So but VR is V minus U. So it is minus K into V minus U cos phi. So now substituting an impulse momentum equation. So mass per second is rho AV into change in the velocity. So the initial velocity is V minus U. Final velocity is minus K into V minus U cos phi. So minus of minus is plus. So V minus U is common. So it comes out. So rho AV into V minus U into 1 plus K cos phi. So now you know that the force is in the x direction. So velocity U is also in the x direction. So work done per second can be written as F into U. So therefore it is rho AV into V minus U into 1 plus K cos phi into U. So now we need, because the water issues from the nozzle, so therefore it has got a velocity. So therefore it is the kinetic energy per second is the input of the jet. So therefore input can always be calculated as half mv square. Since this is calculated as work done per second, this also should be calculated as kinetic energy per second. So it is half mass per second into v square. So entire mass has to be taken. So rho AV will be the formula. So half rho AV into v square. Substituting in hydraulic efficiency, which is output by input. So output is work done per second and input is kinetic energy per second. So that gives rho AV into V minus U into 1 plus K cos phi into U divided by half rho AV into V square. So cancelling rho AV. So we get so 2 times V minus U into 1 plus K cos phi into U by V square. Okay, after deriving the hydraulic efficiency equation for hydraulic efficiency for a given jet velocity and angle phi, the maximum efficiency can be obtained by differentiating efficiency by the velocity u and putting equal to 0. So you know that 2 by v square by 1 plus k cos phi is a constant. So therefore differentiating we get v minus 2u. So that should be equal to 0. So since this term 2 by v square by into 1 plus k cos phi is not equal to 0, so v is equal to 2u. So that means for maximum efficiency, the bucket velocity has to be half the jet velocity. Substituting the velocity v is equal to 2u in the hydraulic efficiency equations, so then we get 2 into, so that is v minus u. So v is 2u, so 2u minus u into 1 plus k cos phi into u. So here it is v square, so it is 2u whole square. So this is, it cancels out. So 2u square, we are left with half into 1 plus k cos phi. So this is about the hydraulic maximum hydraulic efficiency equations. In the previous case where we derived the equation for series of vanes, we had not taken the factor k. In this case we take the factor k, which is accounting for the loss of energy when the flow is glides over the inner surface of the Pelton wheel. So k can be which is generally if it is k is equal to 1, then VR1 is equal to VR. So if k is equal to 0.9 then VR1 is k times VR, which is 0.9 times VR. So k is a factor that accounts for the losses. So now we can say that when k is equal to 1, hydraulic efficiency will be equal to 1 or 100%. When phi is equal to 0, that means the deflection angle is equal to 180 degree. So deflection angle cannot be equal to 180 degree. So that's why this maximum efficiency will, that is getting 100%, is the theoretical value. So actual value will be less than 1. So it can vary from 0.9 to 0.94. So therefore we don't take k is equal to 1. So it will be less than 1, which can be taken as like 0.85 or 0.9 as k. And further, in actual practice, deflection angle cannot be made equal to 180 degree. So in that case, the jet, because if it is made 180 degree, the jet leaving the bucket will strike the next bucket that is coming, and so it causing a retarding force. So that's why it cannot be equal to 180 degree. It has to be between 160 to 170 degree, so that the jet, the angle at the outlet tip will be between 10 and 20 degrees. So that's why the bucket tip angle phi is between 10 and 20 degree, so that the deflection angle is around 160 to 170 degree. So this angle phi is also known as the side clearance angle. Okay, angle phi is also known as a side clearance angle. So this is about the theory part, the equations that are with respect to the Pelton wheel, and how to calculate efficiency. Is been is given in the slides. Okay, so we shall discuss about the designs of the Pelton turbine. The Pelton turbine runner is required to be designed to develop a known power P. So this known power P, that is shaft power, will be given. So when the Pelton turbine is running at a known speed in RPM and a known head H. So how to solve this design steps? So now first step is to determine the required discharge from the relation. So therefore overall efficiency, you know, that is shaft power divided by the kinetic energy per second. Since CV is approximated to equal to 1, so then we can find overall efficiency as P by omega QH. So we can assume overall efficiency is 85%. So knowing overall efficiency, power, specific weight of water, which is 9810, H is known, so Q can be calculated. So now the second step is to calculate the velocity of the jet. So now taking actual value of CV as 0.98, so then V is equal to CV root 2GH. So therefore the velocity of the jet can be calculated. So knowing discharge, knowing velocity, we can calculate what is the total area of the jet, which is Q by V. So now we'll get the total area of the jet. Next step is to calculate, knowing the velocity. In the second step we can calculate, because we have derived that the bucket velocity has to be 0.5 times v, which is a theoretical value, but for design purposes we can take between 0.45 and 0.46 v. So therefore taking u is equal to 0.45 times v, we can find the pitch circle diameter, because u is equal to pi dn by 60. So knowing u, knowing n, so we can calculate the pitch circle diameter. Also for the Pelton wheel, the jet ratio, which is the ratio of pitch circle diameter to the diameter of jet, is taken around 11 to 14. So taking say, like m is equal to 12 or 13, so then we can calculate what should be the diameter, because we know d, so hence small d, that is diameter of the jet, will be capital D by m. So hence knowing the diameter of the jet, hence the corresponding area of the jet is calculated, that is A is equal to pi by 4 d square. So now the total area of the jet is calculated from the third step, and whereas the area of one jet is calculated from the fifth step. So we can find number of jets required. So the number of jets required is total area divided by area of one jet. So now this number of jets can be like 2.82 or 2.7, and we can round it off to 3, and hence the actual diameter of the jet can be accordingly calculated. Also, the empirical formulas for calculating the number of buckets can be calculated as Z is equal to D by 2D plus 15, that is the pitch circle diameter divided by the diameter of the jet divided by 2 plus 15, and the dimensions of the buckets can all be, the width of the bucket is 4 to 5 times diameter of the jet, length is about 2.4 to 3.2 times D, or M is 1.1 to 1.25 times D. So coming to the problems related to the Pelton wheel, the first problem, I will take it very easy. That is to calculate the number of jets, diameter of the jet, diameter of the wheel, that is also called the pitch circle diameter, and quantity of water required is nothing but the discharge. So now here the power developed is given, which is 6000 kilowatts. Net head is 300 meters, and the speed of the turbine is 550 rpm. So here the ratio of jet diameter to the wheel, the small d to the capital D, is given as 1/10. So overall efficiency is 85%. CV is given as 0.998. So then U is 0.46 times V. So knowing these quantities, then we can calculate. So the first step is to from the overall efficiency, that is P by omega QH. Since overall efficiency is 85%, that is 0.85, because P you convert into watts. So that means P is 6,000 kilowatts. So 6,000 into 1000 divided by specific weight of water is 9810 into Q by H into H. So therefore you can calculate Q from this relation, which comes to about 2.4 meter cube per second. So the first step is to calculate the discharge. So now you know CV and you know H, so hence velocity of the jet can be calculated. So therefore V is equal to CV root 2GH. So since CV is 0.98 into root 2GH, so 2 into 9.81 into 300, so we'll get velocity of the jet as 75.19. So knowing the speed ratio is 0.46, which is U by V, so therefore U can be calculated as 0.46 times V, which is V is 75.19, which gives 34.59. So now using the relation for U, that is pi dn by 60, we can calculate the pitch circle diameter. So therefore 34.59 equals 3.14 into D into N is the operating speed, which is 550 given, so divided by 60. So therefore the diameter of the pitch circle diameter or diameter of the wheel is 1.2 meters. So now the jet ratio is given as 10, so therefore the corresponding diameter, the diameter of the jet will be 1.2 divided by 10, which comes to 0.12. So therefore we know the diameter of the jet, so hence the area of one jet can be calculated as pi by 4 into 0.12 square, so which gives the area of the one jet. Since the total area of the jet is to be calculated, which given by Q by V, so therefore the total area. So we know the total area of the jet, we know area of one jet, so total area divided by area of one jet gives the number of jets, which comes to 2.82. so you cannot have 2.82 like this, so you have to round it off, it can be 3 jets, so therefore we make 3 jets. Since the total area has to cannot change, so this is 0.031906, because this is the discharge and the velocity, so therefore we know the total area, so accordingly the D can be actual D can be calculated, so it will be 3 times, because there are 3 jets of so here area of one jet is pi by 4 D square, so it should be equal to the total area, so accordingly D has to be 0.1164, which is not 0.12. So 0.12 was on the assumed ratio like 10. So therefore we slightly change it nearer to this jet ratio, which comes to about 116.4 millimeters. So that was the problem of design, where number of jets and diameter of jet or diameter of the wheel or discharge was calculated. So now we'll give the same problem, which is similar to the previous problem, where you have to assume all the uh, required quantities or missing quantities. So since we have to design a Pelton wheel to develop 1500 kilowatts when working under head of 160 meters and the speed is 420 rpm. So first step is to assume overall efficiency, that is you can always standard value is 85%. So therefore knowing overall efficiency, knowing power 1500 into 1000, so specific weight is 9810 into Q, so into H is 160, so we get Q. So discharge is 1.124 meter cube per second. So now you can assume the value of CV as 0.98, so therefore velocity of the jet can be calculated as CV into root 2G into H. So what is CV? It is 0.98 into root of 2 into 9.81 into 160, so that gives 54.91. So now assuming U is equal to 0.46 times V or 0.45 to 0.46 times V, so we get the bucket velocity as 25.26. So now the using the bucket velocity, we can always calculate the pitch circle diameter. So therefore u is equal to pi dn by 60. So u is 25.26, where equals 3.14 into d into n is given as 420 rpm divided by 60. So where the pitch circle of the wheel diameter will come to 1.15 meters. Now we can assume the jet ratio something between 10 to 14. So therefore I have taken as 12. So jet ratio is 12. So therefore we know that capital D, that is pitch wheel diameter to the diameter of the jet, is 12. So therefore the diameter of the jet can be calculated by dividing pitch circle by 12. So we get 0.096. So therefore since we know the diameter of the jet, the area of the jet can be calculated. The total area can always be calculated by discharge divided by velocity. So which gives the total area. So this total area divided by area of one jet will give the number of jets. Since it is 2.83, so it is approximated to. So that means it is next rounded off to 3. So now there are 3 jets of so area of one jet is pi by 4 d square should be equal to the total area of the jet. So therefore the actual diameter of the jet is 0.0932, which comes to about 93.2 millimeters, not 96 millimeters. So number of buckets can be calculated by the empirical formula, like capital D by 2D plus 15. So therefore the actual diameter has to be used here. So it comes to about 21 buckets. Similarly, the width of the bucket can be 5 times D, diameter of the jet. So 0.466 meters, and also the length of the bucket can be calculated as somewhere around 3 times D, so which comes to about 0.28 meters. So this is about the design of the Pelton turbine. So these two problems were very simple, and we're told to calculate just the pitch circle diameters or diameter of the jet or number of jets on the discharge. So the next problem will be the velocity triangles. So therefore we know the concept of velocity triangles, which were discussed in detail in lecture 5, and also you know how to write the velocity triangles for a Pelton wheel also. So using that concept, now we can solve the problem, the third problem, which uses the concept of velocity triangles. Now here the Pelton wheel has a mean bucket speed, so u is given, so that is 35 meter per second. So when a jet of water is flowing at the rate of 1 meter cube per second, so therefore discharge is given, that the water that issues from the nozzle has got a discharge of 1 meter cube per second. Now under a head of it is working under a head of 270 meters, so therefore the net head is 270 meters, and also the deflection angle is 170 degrees. Since deflection angle is 170 degree, we know that phi is 180 minus 170, which is 10 degrees. So angle of vane at the outlet tip is 10 degrees. So find the power developed by the turbine, means it is work done per second, and also hydraulic efficiency. It is also given as CV is equal to 0.98. So knowing this 0.98, so we can calculate velocity of the jet. So also it is required to determine the overall efficiency if mechanical efficiency is given, okay, which is mechanical efficiency is 80%. Okay, so this is the diagram that you have. So therefore now when the jet issues with the velocity v, when it is about to strike, the vane would have moved with velocity u, so therefore it is striking with velocity vr. So therefore vr is always v minus u. So that's the reason. So first step is to calculate, v is not given here, so v has to be calculated using the data. Okay, so v is CV root 2 GH, so that is 0.98 into root of 2 into 9.81 into H, that is 270, so that gives 71.33. So you know the bucket velocity is 35 meter per second, so that's the reason why we can calculate VR. So VR is V minus U. So therefore it is 71.33 minus 35, which gives 36.33 meter per second. So also we know that since alpha is 0, that is the angle of the jet is 0 because it is issuing in the straight line, and also theta is 0, so therefore it is a straight line, and therefore we have VW, that is velocity of whirl, is V cos alpha. Alpha is 0, so cos 0 is 1, so therefore VW is equal to V. So in all the cases of Pelton wheel, we have VW is equal to V, which is 71.33. Now nothing is mentioned about the losses, so you can assume VR1 is equal to VR, so which comes to 36.33 meter per second. So now you can, when it comes out here, it comes out with velocity VR1. So you can first draw a rectangle triangle. So this entire thing is VR1 cos phi. Okay, so this angle is phi. So since this angle is phi, so this angle is phi. So now you are able to calculate VR1 cos phi. So VR1 cos phi is 35.78. So by the time the jet issues here, the vane would have moved with some velocity u. So therefore you know that u is less than VR1 cos phi. So therefore jet has to leave in this direction. So in this case, particularly beta is less than 90 degree. So in this case, VW1 is VR1 cos phi minus U. So that's the reason why we have used VR1 cos phi minus U, which comes to 0.78 meter per second. You know the work done formula, because beta is less than 90 degrees, so we are using plus sign. So rho AB into VW plus VW1 into U. So where rho is 1000 kg per meter cube, A into V, we don't know the diameter of the jet, so that's the reason why AV is written as discharge, so that is 1 meter cube per second. So VW, knowing VW1 and U, so we can calculate work done per second. Dividing by 1000, we get 2523.85 kilowatts. Now what are the water issues from the nozzle and has got a kinetic energy. So therefore since work done is calculated per second, so also kinetic energy per second. So we get this formula half rho AB into V square. So therefore half into 1000, A into V is nothing but 1 meter cube per second. Therefore we have V square term here, 71.30 square, and dividing by 1000 we'll get kilowatts. So you know that hydraulic efficiency is work done per second divided by kinetic energy per second, which comes to 99%. So knowing hydraulic efficiency and knowing mechanical efficiency, we can calculate overall efficiency. So which comes to 79%, 79.4%. So this is how we solve the problem. So we take another simple problem related to the same problem as this. So therefore now here in the previous problem the bucket speed was given, and in this case the bucket diameter is given as 0.8 meters and is running at 1000 rpm. So that using this data it will enable us to calculate the tangential velocity. So tangential velocity is pi dn by 60. So pi is 3.14, d is 0.8, n is 1000 rpm. So therefore we can calculate u. So knowing CV and the net head, so we can calculate velocity, which is CV root 2 GH as 86.82. So now next is similar. So we have V, knowing V, so we can always calculate VR. So VR is V minus U, so that gives 44.95. So we know that VW is V cos alpha, alpha is 0, so therefore VW will be equal to V, so that is 86.82 meter per second. So nothing is mentioned about the losses, so VR1 can be taken equal to VR as 44.95. So therefore VR1 cos phi can be calculated and compare with U. So in this case VR1 cos phi is greater than U, so the time the jet issues as VR1, so the vane would have moved with velocity U. So therefore since U is less than VR1 cos phi, so therefore the jet will leave in this direction. So therefore in this case beta is less than 90 degrees, so therefore we are using plus sign for work done per second. So therefore we have work done per second as rho AV into VW plus VW1 into U. So that gives A into V is nothing but the discharge, A into V is nothing but the discharge. So therefore rho into AV into VW plus VW1 into U. So dividing by 1000 we get 555.01 kilowatts. So that is nothing but the power developed by the turbine, which is 555.01 kilowatts. So they have also asked what is the power available at the base. So the power available at the base can be calculated as that is WQ into H, where W is specific weight of water, which is 9810, Q you know 0.15, and H is 400. So that gives 588.600 watts. Dividing by 1000 it is 588.6. That means before it issues from the nozzle, what is the power is calculated from this formula. So but after it issues from the nozzle there is always some loss that takes place, so that is nothing but the kinetic energy. So therefore there is always a difference between at the entrance to the nozzle is 588.66, by the time it goes into the nozzle and comes out, so there is some losses that is taking place. So therefore kinetic energy per second is calculated by this formula, which is half rho AB into V square. So we get 565.33 kilowatts. But hydraulic efficiency is nothing but work done per second divided by kinetic energy per second, which comes to 98%. So many of the textbook use this formula, which is WQH, which is actually wrong, because this formula can be used only, that means you can use it for kinetic energy only when CV is equal to 1. If CV is equal to 0.98, so then definitely there will be a difference between these two quantities. So therefore for hydraulic efficiency, it is always work done per second divided by kinetic energy per second, not actually WQH. So these things are shown in the by means of a figure. So when you come here, before it enters the nozzle, so we have the power. So that power is calculated by WQ into H, which comes to 588.6. So once it enters the nozzle, there is always some loss. So therefore it comes out, this output, this is input. So therefore there is some loss, that is kinetic energy per second. So loss in the nozzle can always be calculated as power at the base of the nozzle minus kinetic energy, which is 23 kilowatts. It goes as a loss in the nozzle. So now I can show you that if CV is equal to 1, we know that V is equal to CV root 2GH. If CV can be put as 1, then it is simply root 2GH. So we can square both sides, then V square is 2GH or H is V square by 2G. So if you put it in the kinetic energy formula, half rho AV into V square. So rho AV is nothing but Q, where V square is here V square. So now for the mass density, you put it as specific weight by G, so that gives V square by 2G as H. So therefore the formula becomes WQ into H. So therefore only when CV is equal to 1, then only kinetic energy per second will be equal to omega Q. That means the power at the base of the nozzle will be equal to kinetic energy per second, which is both are same, assuming that there is no loss in the nozzle. So that when that happens, when CV is equal to 1, CV will always account for the loss. So if you take 0.98, so there is always a difference between these two quantities, which is shown by means of this example. So that's why I have shown for this previous problem, I have shown by the example like CV is equal to 1, then there is no loss. So kinetic energy can always be calculated as WQH. So for the above problem, if you had taken CV is equal to 1, then you would have divided by the power at the base of the nozzle, which actually comes to 94.3. But actually, if you take CV is equal to 1, then it is 94%. But if CV is equal to 0.98, then you got 98%. So we have to use here kinetic energy. Okay, so that's how the calculations are shown. If CV is equal to 1, then V is equal to 88.58. Using CV is 1, so then you can use this in kinetic energy. So that is also, see this answer, by using this formula we have calculated kinetic energy as 588. By using WQH also we are getting 98. So that's by using WQH also we are getting 588.6. So that's why this happens only when CV is equal to 1. So if CV is equal to 0.98, so you cannot use it, this formula. So you have to use kinetic energy per second. So note the difference in the next problems. When we solve such type of problems, you should be able to identify what is the concept of CV and why there is a difference between the powers at the base of the nozzle as well as the power at the after it comes out of the nozzle. So now take up a problem of that is the two jets that is striking the buckets of a Pelton wheel, which is having a shaft power of 14715 kilowatts. So diameter of the jet is given, so 150 millimeters. Net head on the turbine is given as 500 meters. We have to find the overall efficiency, where we have given CV is equal to 1. So now velocity of the jet can be calculated. V is equal to CV root 2GH. So that is CV is 1 into root 2GH. So a net head is 500. So we get 99.05. So now using the velocity and the diameter, we can find what is the discharge of each jet. So which is pi by 4, 0.15 square into 99.05, which comes as 1.75 meter cube per second. But there are two jets striking the Pelton wheel. So that's the reason why total discharge is calculated by multiplying by 2. So therefore the total discharge is 3.5 meter cube per second. So 2 times 1.75 gives 3.5 meter cube per second. So now you know the overall efficiency is shaft power divided by kinetic energy per second. I have used WQH in the reason that it is CV is equal to 1. Otherwise you can also use as kinetic energy per second formula. So but if we can use WQH provided CV is equal to 1. So therefore P is known, shaft power is known. So multiply by 1000 to convert into watts. W is 9810, which is specific weight of water. So Q has to be not 1.75 because two jets are striking. So total discharge has to be taken here. So the net head, the Pelton wheel is working under a net head of 500 meters. So we get overall efficiency as 85.7%. So those five problems were based on that the net head is given, and I take a few problems like one or two problems on on the Pelton wheel, such that we have the gross head given, where the some data are given to calculate the head loss due to friction, or head loss due to friction will be given, so that you will be able to calculate the net head. Otherwise, the problem remains the same as the previous problems. Uh, where we are required to find what is the power given by the water runner, that is work done per second, and hydraulic efficiency. We have solved such problems, except that their net head was given. So now gross head is given. So now it is the penstock supplies water from a reservoir to the Pelton wheel with a gross head of 450 meters. So therefore the gross head is given. One third of the gross head is lost in friction. So the head loss due to friction is one third of 450, which gives 150. So therefore you know that gross head minus head loss due to friction is net head. So therefore net head is calculated. So using this net head, we can go for the calculation. That's the change in the problem. So rate of flow of water is 1.8 meter cube per second. So discharge is 1.8. So your angle of deflection is 170. Therefore phi becomes 10 degrees. U is given as 0.45 times V, and CV is 1. So first step is to calculate net head. So that gives gross head minus head loss due to friction. So 450 minus 150 gives 300. Using this 300 as a net head here, so we can calculate velocity of the jet. So velocity of the jet comes to 76.72 meter per second. So knowing velocity of the jet, we can calculate U, that is velocity of the buckets, as 0.45 times 76.72, which comes to 34.52. So now we can draw the velocity triangles. So a velocity triangle, like a straight line, is drawn at the inlet, which gives layer. So here this is V, and now the bucket velocity is drawn. So the difference is VR. So VR is V minus U. So therefore 76.72 minus 34.52, which gives 42.2 meter per second. So we know that VW is V cos alpha. Alpha is 0. So therefore VW is V. So that is 76.72. So no losses given. So we can assume VR1 is equal to VR as 42.2 meter per second. So next step is to calculate VR1 cos phi. Okay, so VR1 cos phi. So phi is 10 degree because deflection angle is 170 degree. So we get VR1 cos phi. We definitely U is less than VR1 cos phi. So VW1 can be calculated as VR1 cos phi minus U. Okay, 7.04 meter per second. So now the power given to the runner is work done per second, which is given as the mass per second into VW plus VW1, because beta is less than 90 degree into U. So therefore rho is 1000, A into V is discharge, so it's 1.8 into you know the value of VW, we know the value of VW1 and U. So therefore the work done per second is calculated. You can divide by 1000. So work done per second is 5204.51 kilowatts. Also kinetic energy per second, you might be wondering that why I have used WQH. Here in this case CV is equal to 1, so therefore I have used WQH. You can also use half rho AV into V square. You will get the same answer, 5297. So therefore using WQH, so specific weight of water is 9810, Q is given 1.8 and H is also 300 meters. So we can calculate kinetic energy per second. So therefore work done divided by the kinetic energy per second gives hydraulic efficiency, which is 98%, 98.25%. There are few problems where you can calculate the diameter of the pipeline or penstocks and diameter of the jet. This problem is related to that. Okay, so that's the, and there are a specific case of a turbine where it has 2 runners and 2 jets per runner. So that's the additional data which is given. So we have totally 4 jets here. So carefully we have to solve this problem. So now water available for the Pelton wheel is 3.5 meter cube per second, and the total head is, that is gross head, is given 240. Turbine has 2 runners and 2 jets. Okay, all 4 jets have the same diameter. So pipeline is given, penstock length is given. The pipeline is 2700 meters, and efficiency of power transmission is given, which is 92%. And efficiency of each runner, that is hydraulic efficiency, is 90%. So we can take CV as 0.98 and coefficient of friction is 0.02 to calculate head loss due to friction. So it is required to find out what is power developed by the turbine, diameter of the jet, and diameter of the pipeline. So now what is efficiency of transmission? This will be helpful for you to calculate the the net head. So now when the water comes from the reservoir and moves into the penstock as well as the nozzle, so therefore at the end of the nozzle we get a net head, because when the water flows, so there is always some loss that is taking place. So whatever that power available at the end of the nozzle is nothing but like net head, and starting we have the gross head. So therefore the output is nothing but the net head, whereas the input is nothing but the gross head. So therefore efficiency of power transmission can always be written as net head divided by gross head. So efficiency of transmission is given as 0.92. So equated to H by 240, which is gross head. So therefore H is 0.92 times 240, which is 220.8. So that means 0.08, about 92%. The 0.92 is 92%. So therefore 8% is goes as a loss. So that's how you can directly calculate head loss also. But anyway, we have calculated the net head. So from gross head, if you deduct net head, you will get the head loss due to friction, which comes to 19.2 meters. So this is how you calculate using the efficiency of power transmission. Okay, and using this formula, so where you are able to calculate the out of 92% of the gross head comes as a net head, 8% will go as a head loss due to friction. So therefore it is 19.2 meters. So knowing the net head, now the calculation goes as like V is equal to CV root 2 GH. So therefore 0.98 root of 2 into 9.81 into 20.8, so that comes to 64.5. So you can calculate kinetic energy per second, because half rho AV into V square. So here so Q is 3.5. So V is known, velocity of jet. So therefore, so when you take the total discharge, you will get the total power developed. So that is what asked. So if you, by chance, if you take one discharge, there are 4 jets, and you divide by 4, and then you will get power developed. Okay, so if there are 2 runners, then you have to divide by 2 and use it, and then multiply by 2 for the power developed. So that's why I have taken the total discharge 3.5 and calculated the total power at one shot. So that's the reason why we have taken the total discharge. So therefore we get 7280. So which we can use the formula for hydraulic efficiency, which is power developed by kinetic energy per second. So kinetic energy per second is known, hydraulic efficiency is known. So therefore power developed by the turbine can be always calculated, 6552.4 kilowatts. So now the diameter of the jet is to be determined. So in order to calculate diameter of the jet, there are 4 jets. So total discharge is 3.5. So therefore 3.5 divided by 4 comes to 0.875. So using the diameter discharge of each jet, then you can calculate diameter of each jet. So velocity of the jet is 64.5. So hence diameter of the jet can be calculated. So at any point of time you should not put 3.5, which will be wrong, because there are 4 jets here. So therefore the total discharge has to be divided by 4. Now for the diameter of the pipeline, when the water is coming from the reservoir, the entire water comes through the pipeline. So that's the reason why while calculating for the pipeline diameter, you should use total discharge. Okay, so here you should not commit mistake. So nowhere at 0.875 should be used here, because the water comes from the pipeline and gets divided into 4 jets. Okay, so that's why here total discharge has to be used. So HF is FLV square by 2GD. So FL by 2GD, but velocity is not the velocity, this velocity, because this is the velocity of the jet, but this velocity is the velocity that is flowing in the pipeline. So velocity of water flowing in the pipeline. So therefore what is velocity? Is discharge divided by area. Which area? It is the area of the pipeline. So therefore discharge divided by area of the pipeline. So V square, so square. So now you get this formula, FLP square 2GDP by pi by 4. So it raised to the power of 4. So that's why it is raised to the power of 4 into another d. So that gives dp to the power of 5. So therefore you can, solving this, knowing head loss due to friction, you can always calculate the diameter of the pipeline. So that's how the problem is quite different from the previous problems, except that here the 4 jets are there. So therefore while calculating the diameter of the jet, you have to divide by 4 and then calculate diameter of the jet. But when you are calculating diameter of the pipeline, the entire discharge comes first through the pipeline. So that's why the total discharge has to be taken. So it is not the velocity of the jet here, it is the velocity of flow in the pipeline. So that's why I denoted as Vp square, Vp. So FLV square, so Vp square. So similar problem we have again, but there are three Pelton wheels. Okay, three single for each Pelton wheel a single jet will strike. So there are three Pelton wheels. So for three Pelton wheels a pipeline comes and will be that pipeline will be supplying water to three Pelton wheels. So head above the nozzle is, that is, gross head is 360 meters. CV is given as 0.98. Coefficient of friction is 0.02. Overall efficiency is 85%. So specific speed of each turbine is given. So that's the extra term that I am given. So specific speed is the speed of the turbine, a geometrically similar turbine, when working under head of 1 meter will develop 1 kilowatt power. So when you construct a model and then try to operate under a head of 1 meter, okay, 1 meter, and it develops 1 kilowatt power, but the corresponding speed of that model will give as specific speed, which is 15.3 rpm. So head loss due to friction is already directly given as 12 meters. Now the operating speed of actual turbine is 560 rpm. So to find what is the total power developed, diameter of each nozzle, that is diameter of the jet is, now nozzle means it is diameter of the jet, so diameter of the pipeline and discharge. So this is the problem. Okay. So now the gross head is given, which is 360, but the head loss due to friction is directly given. So that is 12. So therefore you can find the Pelton wheels are operating under a head of 348 meters. So we have a formula that is derived, that is specific speed is n root p h to the power of 5 by 4. So p will come in kilowatts. So therefore if specific speed is given as 15.3 rpm, substitute here. N is the operating speed, which is 560, root of p. Okay, so divided by 348 to the power of 5 by 4. So P comes out in kilowatts. So therefore the answer is 1686 kilowatts. So now you know that this is the power developed by each of the turbines. So there are three Pelton wheels, so therefore it gets multiplied by 3. So therefore the total power can be calculated, so which is 5059 kilowatts. So knowing the head in each of the turbine, so we can calculate velocity of the jet. So CV root 2GH. So therefore 348 is the net head. So velocity of each of the jet is 80.98 meter per second. So now you know kinetic energy per second, which is half rho AV into V square. So half A into V is nothing but Q. So now, so in order to calculate overall efficiency, we know that this is the shaft power, that is what we calculated in the previous step. When we use total power, because for overall efficiency you should use total power, so then this will give the total discharge. So this Q will give the total discharge that is coming from the penstock. Okay, so this Q will be it will be from the penstock, and which will get divided into three parts as the jet later on. So we are not interested in that. So here this Q will give you nothing but, which is the total discharge from the in the pipeline. So using overall efficiency, so now using overall efficiency, which is given was 0.85, so now we can calculate Q. So that gives total discharge. So total discharge is 1.815 meter cube per second. So this total discharge has to be used in the formula for the head loss due to friction, FLV square by 2GD. You know that velocity in the pipeline is Q divided by area. So that gives the diameter of the pipeline. So this is how you calculate the diameter of the pipeline. Similar problem, but except for few changes in the problem, which we have seen in this problem. So diameter of the jet, you know that there are three Pelton wheels. So therefore the total discharge that is coming through the penstock gets divided into three parts. So therefore in order to calculate the diameter of the nozzle, so we have to divide by 3. So this much discharge will pass through each of the nozzles. So that's the reason why we have discharge that is through each jet, that is of each jet is 0.605 pi by 4 d square. So this is nothing but the velocity of the jet is known. So therefore we can calculate the diameter of the jet, which is also known as the diameter of the nozzle. So Q is calculated, diameter of the jet is calculated, diameter of the pipeline is calculated. So that is what asked, and the power developed is calculated. So water comes from the from the pipeline, and then issues through the, so here there is a discharge coming over. So there is a discharge, like the same discharge passes through the nozzle. So therefore you know that by continuity equation you can know that pi by 4 this diameter, pi by 4 d square dp square into velocity vp, like this. So which should be equal to pi by 4 d square, that is diameter of the jet here, d square into v. So velocity, this is v now. So after it comes out of the nozzle, it will become V here. Before it will be Vp. So therefore, we get a relation between Vp and P now. So because the diameter of the pipeline is known, diameter of the jet is known, so the relation between Vpa and V can be calculated. So now HF is FLV square by 2GD. So therefore we know that friction factor is 0.032, length of the pipeline is 4000, and diameter of the pipeline is given. So now we get HF in terms of Vp square. You can substitute this entire thing here and get in terms of V square. So now you know that V is equal to CV root 2GH, but CV is not given, so I have taken as 1. So 1 into root 2GH. So this V in terms of H you can substitute. So that gives HF in terms of H. So now you know the relation head loss is nothing but gross head minus H. So therefore head loss is in terms of H. H1 is 400 minus H. So H is unknown. So H can be calculated. Okay, so that is 375.68. So now the gross head is 400, whereas the net head is 375. If you take the difference, you will get the head loss. So this is how you. So now you know, knowing the net head, so we can calculate V, then U, which is 0.45 times V. So VR is V minus U. VW is V, that is 85.85 meter per second. So VR1 is not VR, so it is 0.85 times VR, so hence can be calculated. So next step is to calculate VR1 cos phi, so and compare with U. So definitely VR1 cos phi is greater than U, so therefore VW1 is VR1 cos phi minus U. So that is the calculation step. So work done per second is rho AV into VW plus VW1 into U. So substituting the values, okay, so now the diameter of the jet was given, so it is pi by 4 d square, 0.15 square. Velocity is known, 85.85, which is calculated here. So then VW is known, VW1 is known, and U is calculated. So therefore dividing by 1000 we get, okay, 5036.92 kilowatts. In order to calculate the shaft power, since we know the work done, mechanical efficiency is also known, we can make use of the equation mechanical efficiency. Mechanical efficiency is shaft power divided by work done per second. So since work done per second was calculated, hence it enables us to calculate the shaft power. So in order to calculate hydraulic efficiency, we have already calculated work done per second. So therefore, we'll calculate kinetic energy per second. So kinetic energy per second is half rho AB into V square. So half into 1000. Area is pi by 4 d square, diameter of the jet is given. So velocity into V square is V cube. So therefore velocity of the jet is 85.85. So dividing by 1000 we'll get the kinetic energy per second. So work done per second divided by kinetic energy gives hydraulic efficiency, so 90%. So now you know that overall efficiency is mechanical efficiency into hydraulic efficiency, so which can be calculated, and hence it is 76.62%. So this is the problem which makes use of the data to calculate the net head. Little tricky problem, but still you are able to calculate. So this will be the last problem in the Pelton wheel, where we should be able to calculate what is the power lost in the nozzle as well as the power lost due to hydraulic resistance in the runner. So here head at the base of the nozzle is given, that is 80 meters. Diameter of the jet is given. Discharge is 0.3 meter cube per second. Power at the shaft is 206 kilowatts, and power absorbed in mechanical resistance is 4.5 kilowatts. So you should understand this block diagram, where the power at the base of the nozzle, that you know. So this is the nozzle. So now here the power is WQH. Once it comes out, then it will become kinetic energy. So therefore input is WQH, output is kinetic energy. So whenever the water flows through the nozzle, there is always some loss. So that is the power lost in the nozzle. So in order to calculate power lost in the nozzle, kinetic energy that is WQH minus kinetic energy will give the power lost. So once the kinetic energy which is that is issued from the nozzle will strike the buckets, so therefore work is done. So in this process there is some loss that takes place, the hydraulic losses takes place, so therefore the power is lost due to hydraulic resistance also, and this work done per second is is utilized to develop the shaft power. So in this case there is some power that is lost in some bearing friction, so therefore that is known as power lost in the mechanical resistance, which is given here. So now So in order to calculate power lost in the nozzle, so you should calculate this particular term, so which is WQ into H. So since head at the base of the nozzle is given, so now we are able to calculate WQH. So W is 9810, Q is 0.3 and H is 80, so that gives 235.44 kilowatts. So next step is to calculate the kinetic energy per second. For that energy per second, we need velocity. So you know, discharge is nothing but area of the jet into velocity. So but the diameter of the jet is given, so therefore pi by 4 d square, so that enables us to calculate the velocity. So velocity is 38.22. So using this velocity, you can calculate what is kinetic energy per second. So kinetic energy per second is half rho a v into v square. So rho is 1000, a into v is discharge, so therefore velocity is 38.22 square. So dividing by 1000, you will get 219.12 kilowatts. So now you know WQH and you know kinetic energy per second. So therefore that is the power lost in the nozzle is nothing but power at the base of the nozzle minus kinetic energy per second, which comes to 16.32 kilowatts. So knowing kinetic energy per second, if you deduct power loss due to hydraulic resistance, you will get work done. From work done, if you deduct this power lost in the mechanical resistance, then you will finally get the shaft force. So now we know the kinetic energy per second, which is 219.12. Power lost is to be determined. So power lost is to be determined. Okay, so this power loss in mechanical is given, but shaft power is already given in the problem, which is 206. So rearranging this term, so we'll find power loss to hydraulic resistance as 8.62 kilowatts. So this is how we solve the problem. So that's like this, any combinations can be given in this type of problems. So we have discussed in detail about what is Pelton wheel, what should be the shape of the buckets, and what is the equation for work done per second. And then also we discussed about what should be the phi angle at the outlet tip, and also about the deflection angles. So in this case, the phi angle should be between 10 and 20 degrees, whereas deflection angle has to be between 160 and 170 degrees. So that's how. So you should also know how to draw the velocity triangles at the outlet. So and then make use of the formulas in the work done per second and kinetic energy per second. I also told you that when CV is equal to 1, kinetic energy per second will be always equal to WQ into H also. Like this, we also know that how to calculate the diameter of the jet or diameter of the pipelines. So diameter of the pipelines can also be calculated by HF is equal to FLV square by 2GD. So we have to be very careful to take what velocity of flow in the pipeline, which is not same as the velocity of the jet. So that is different, and the velocity of the jet is different. So water after it issues from the nozzle, which got the velocity where the velocity of the jet is definitely more than the velocity of the pipeline. So that's why you have to be very careful here. So how to calculate the diameter of the pipeline. So this is about the Pelton wheel, and hope you will go through all these slides and my video lectures. And if you have yeah, you can it's all self-explanatory. Go through each one of the slides that I have told, and concentrate on what I have told, the concepts, and it will help you to solve any type of problems in Pelton wheel. See you in the next session. That is, I will be covering the on reaction turbine. Specifically, first I will take Kaplan turbine, and then I may go to the inward reaction flow turbine. Okay, thank you very much.